Hi, in this video I'm going to discuss the hydrolysis of acetals back to a ketone or an aldehyde. So if you remember from the previous video of acetal formation, we went from, we had that aldehyde, and using ethylene glycol and a catalytic amount of acid, we got our acetal, which could be used as a protecting group. But anytime you install a protecting group, you have to be able to remove that protecting group. So that's what the hydrolysis is. It's going from the acetal back to our original aldehyde or ketone. And in this case, we only need to use water. Water is the only reactant for us to go from the acetal back to the ketone or the aldehyde. So I'm going to go ahead and show the mechanism of how this works. What you'll notice when I go through the mechanism is it's the same exact intermediates, just in the reverse order. So we're using water and we have the protonation steps, the leaving groups, everything just goes in the reverse order. So starting with our acetal. And don't be confused by this having the OR and the OR. Remember, we have the cyclic acetal like up here, which is the protecting group, but then the acetal can also just have two oxygens with an R group on each of them too. So first step is going to be a protonation. And in this case, we're in acidic conditions. So we're going to protonate with hydronium that's formed from the catalytic amount of strong acid. So we protonate to get our now protonated alcohol group. You can think of it as an alcohol group at this point, R group with a hydrogen bonded to that oxygen. So now we're going to have our first leaving group. That's going to get kicked off since it's a great leaving group now with a positive formal charge. And now we've formed our next intermediate. We're going to undergo nucleophilic attack now, but given we're in acidic conditions, our nucleophile is going to be water, not hydroxide, like if we're basic conditions. So water comes in, the electrons from that double bond move up to the oxygen, so now we have this intermediate, and we've got to deprotonate that hydrogen from the OH2 group, and we'll use water to deprotonate. Since again, we're in acidic conditions, so no hydroxide, and I'll get now this intermediate. And if you remember, this is my hemiacetal. So when we formed the acetals, there was 8 steps total? 7 or 8 steps, And we formed the hemiacetal as one of those. So now we're going the reverse direction, and we've got the hemiacetal. So what we need to do is we need to now get rid of this OR group, because our ketone obviously doesn't have an R group bound to the oxygen. So we need to protonate that oxygen. So we'll protonate with H3O+. To make a good leaving group now. So lone pair from the oxygen moves down, kicks off the ORH group to give whatever that alcohol would be, right? So if the R group's a methyl, it would be methanol, it could be ethanol, etc. So we're left now with almost our final product. We just have to deprotonate this to get back to the aldehyde. So deprotonate, as we've been doing for this whole mechanism, with water, and we end up with our final aldehyde product. But notice all these steps are equilibrium, so I can just reverse the direction, and it's the same exact mechanism that we went over before. Because all the steps are in equilibrium with this reaction, all you're doing is having the same intermediates and just reversing the order of everything in your formation of the acetal and then hydrolysis of the acetal back to the ketone or the aldehyde. Now the same is true to the enamines and imines. So I'm not going to go through the mechanisms for both of those, but it's the same thing as the acetal, just the reverse order. So I challenge you, practice on your own, going in the opposite direction from your imine or your enamine back to your initial reactant. Because it'll be the same exact process that the hydrolysis of acetal groups was.